Oh, Alia.
Yeah. Hello, Professor.
Here, I just watched the get your water and now you can have it here. And I'm gonna hit this and we're gonna see what goes on. All right, so this last day on Thursday, this is probably what you saw. It's loading.
Oh, we are 4 of us. No, 3 of us. Others.
My wife has the laptop today, so I'll be without a.
Oh, I see.
Yeah, without a
So
camera.
you guys have to share, huh?
Yes. Mm-hmm.
Challenges of online. Huh?
Yeah. If it was a long-term thing, I guess we'd just invest in another laptop.
No, understandable. Yeah. So back in my country, like where I'm from, India,
Mm-hmm.
so there also the school is being held online, and there you cannot expect everyone to have. So there the expectation is to have phone, not a laptop. But even that is asking too much. So they have a channel, the whole TV channel for this.
Oh, okay.
On a channel, and which means that TVs are a lot more common. And if you don't have it, then you have to go into another house and have it, I suppose. Yeah, I don't know how these things work. Yeah. And just imagine if there are 2 kids in the house, I don't know how it works.
Picture in a picture.
Yeah, picture in a picture, right? Yeah, olden days used to have that. Yeah. Okay, we are 4 of us. Moses is missing. Yeah. Khaled is absent last time also. Okay. I did post a homework, correct? Yes. Homework.
Yeah, on complex numbers.
Yes.
Yeah.
The contents for that you should be able to do it from the previous 2 classes. Jordan, you missed last class, so just look into the recordings and that should be good enough.
Yes.
If you're seeing complex number, it's mostly review, except I have a little more detail about the cubic roots, a little more detail. I plan to maybe, since the homework is already done, maybe there might be some problem related to a more involved cubic root. So that's what primarily it comes about. In fact, the whole complex numbers were discovered, or what do you call it? It came into the literature in the process of solving a cubic roots of a cubic polynomial, the roots of a cubic polynomial. We have homework 4. September 22nd, that's a Tuesday. And midterm 2, October 8, Thursday. Again, midterm 2 is scheduled to be in class, unless there is a good enough reason. So this will be in class, pretty much like midterm 1 also, but then we canceled, made it take home. So the same thing here. Be prepared to be in class, but things can change. Okay. Actually, having said that, I was looking into your midterm 1. I wanted to grade it yesterday, but I should say that I was not completely satisfied with the work. It seemed to me that you guys knew the answer and you were forcing to get the answer correct. And it seems to me that if the answer was not there, if you were not provided with the answer or you didn't have access to the answer, then probably most of you would have struggled or wouldn't have been able to do that. So that's something you need to work on, which means that the main content of the topic was not grasped, which is my failure too. But I just wanted to mention that. So I might be a little strict, or it might seem like I'm being hard on the grading. So be aware of that.
Can you give an example of what do you mean exactly?
Oh, what I mean is the first problem is what bothered me. I didn't look into, after that I didn't even look into the rest of the problems because I thought the rest would be worse. So for example, I gave the question was this, I suppose, right? Phi hat is equal to, the answer is, I'm based on how your work, I didn't actually work it out. I think it is r hat, or is it minus sine theta?
I thought it was minus sine theta r
Sine
hat
theta, yeah.
minus cosine theta.
I remember this because they've done this struggle actually. And this is theta hat, I suppose, and plus 0 phi hat. Now, almost everyone tried to get the, or assume that the right hand side is this and try to get this. In fact, you have to get it the other way, right? So if you do phi hat over phi, you do get, first thing you see is that, oh, this is minus, what is this, minus cosine phi, this is rho hat, right? So this is minus cosine phi in the I direction, of minus sine phi in the j direction. And now, if you don't have this in front of you, but you still want to write it in terms of spherical coordinates, you want to write I and j in terms of the spherical coordinates. So that's the inverse process that you want to do. So basically, first you want to write I is equal to, so, or how do you say this? So let me put it like this. So r hat is sine theta cosine phi. I hat plus sine theta sine phi. J hat plus cosine theta k hat. Theta hat is equal to, I think it is, help me here. So this
Cosine theta cosine phi I hat plus cosine theta sine phi j hat minus sine theta k hat.
Minus sine theta. And phi hat is phi
Minus,
hat.
minus sine theta I hat plus cosine theta j hat.
Okay. So basically, once you have this, you basically have to invert this whole thing. Like think of this as variables if you want. That's one way of looking at it, but best is even to take the dot product, right? How do you invert vector? You take dot products of this quantity. So, and then you get I hat, j hat, and k hat in terms of r, theta, and phi. And then substitute it in there and get it. That would be a logical way of going about it. But now it becomes hard for me to grade because all of you got the answer because you knew what the answer is. In fact, it was very clear from what you were working on that it is you were trying to get the answer. Again, I'm not pointing at a particular person here. At least that's the overall feeling I had from
So,
looking at your work. Yes, Darren, you were commenting?
yeah, so I solved it by just system of equations.
Yeah, these are system equations, right? So,
Okay.
for example, if you want to undo it, so if you want to solve for ijk, these are systems of equations pretending that this is given to you. Or mostly how you do this is, so you want to write it in terms of the best way to do this is the formal way would be, is 1 times I, correct? That's a trivial statement. But then now put r hat plus theta hat plus phi hat. That's a correct statement, and you immediately get r hat dotted with I hat times r hat plus theta hat dotted with I hat in the theta hat direction plus phi hat dotted with I hat in the phi hat direction. R hat dotted with I hat, you know what that is. It's so when I dot it with I hat, it's only this term that's going to survive. So that's sine theta cosine phi in the R hat direction. Theta hat, it will be this that will survive. So it's cosine theta cosine phi in the theta hat direction, and minus sine phi in the phi hat direction. But if you have solved using the 3 unknowns, that's perfectly fine. But this is a more standard way of doing it. You will see this in Fourier transform or any vector space. Whenever you want to solve for the components, you put in a complete set and then get the components out. But if, for example, if this was an infinite dimensional space, then it might be hard for you to do this whole inversion simultaneously. So in this case, it works out because it's 3 by 3 matrix. But that's okay. If you have solved for IJK, that's also, at least as far as I'm concerned, for this exam, that's okay. Yeah. So that's my only complaint in there, and I felt that other problems also, that must be the same story. So I was a little disappointed, and then I just thought I'll grade it later. So that's my small comment on it. So at least I was thinking that I'll be hard. It depends whenever I grade it, how it is going to be. It's like the challenge here is that if the answer is correct and method also is roughly correct, how do you take away points? It's a little harder to justify that process. So that's fine. That's why I stopped. So I had to come up with a good strategy to grade. Yeah. Any comments or any general things you want to say?
Yeah, I when I was doing this problem, so I took the derivative and then I saw that there was no k hat in like d phi hat d phi.
Uh-huh.
And so it seemed like pretty clear that like r hat and theta hat, like that contribution of the k hat had to cancel out.
Yeah, so, okay.
So it seemed almost like,
Yeah.
yeah.
So for example, let's say, I think maybe this is what you're meaning. So I don't know. So for example, this is a sphere, right? Our hat here is this, and theta hat here is in this direction. And that is a direction here. And rho hat, so this is basically rho, right, in the direction perpendicular to this. So this is where this sits. So that's your derivative, if you want. That's rho hat, which is a derivative of that you're probably mentioning. And there, it seems like, yeah, there might be a triviality in here that geometrically you can see that. So that's why I want to see your work closely and see how much visualization there was. So that's my challenge, that how do you see, how do you grade when, yeah, I hope it makes sense, yeah.
Right. I guess what I'm saying is, like, it seemed like once you had the derivative, it seemed pretty easy to do algebraically. So I didn't think to like insert.
No, don't take, I'm not, again, don't take personally into anyone's solution. I'm just saying it doesn't have to be this way. I mean, this is one way of doing it. I'm not saying that I will penalize on that. Even if you solve for that, that's okay. I will look into the work in particular, but it seemed to me overall, on an average, when I looked at it, that's the impression I got. Like, I don't want to pinpoint anyone's work here because I haven't looked into it in too detail. I would say that I was disappointed a little in the sense that I felt, or the impression I got was that since the answer was there, it was easier, kind of. Like if it was an in-class exam, for example, probably it seems to me that you would have struggled. Again, not personal. It's not a personal comment on anyone.
It struck me as an easy problem. And maybe I didn't solve it the way you intended for us to solve it. And I didn't do any visualization geometrically. So I'm sure I missed like the point of the problem in solving it the way that I solved it. But it didn't seem, yeah.
Yeah, so that's where the challenge would be. So I will come up with a way to grade. And it might seem in this kind of grading, sometimes often it happens that, I was penalized even though I got the answer. So let's wait for the grading. So that's why I have to come up with a strategy.
Sure.
And I can justify that, oh, this is not. Like doing a different method, usually I don't like to penalize. So that you should criticize. But doing, I want to somehow penalize for not having the answer having helped you. I don't know how I will do that.
Right. So I think like for this problem in particular, I don't think I was helped by having the answer available.
Okay.
Yeah,
like,
I would say the same thing.
Like for number 2 with the delta functions, like I think when I was taking the integrals, I like messed up some of the prefactors, and then because the answer was there, I was able to see, oh, like I was off by a factor of 2 here or whatever. So I think that like in that problem, I was helped by like seeing the prefactor of the delta function. But I think for this problem, I wasn't really helped by the fact that we had the answer.
That's fine. Yeah, yeah. But yeah, again, maybe I'm commenting too early. Yeah. So let's wait and see. Yeah.
Yeah.
Okay.
I think I agree with your premise, but I don't think this problem is the issue.
Yeah, I mean, you know only your work, right? I've seen everyone's work.
That's true. That's true.
So you might be over. Like again, it is not a personal point. I did say that it's overall, that's the impression I got, but I'm not saying anyone's particular work. Okay. Yeah. Sorry about that negative comment. And again, I'll I'll see what I can do. Okay. So let's do complex analysis. This is, I think, a nice concept. It's called an analytic function. So this is called, this is, yeah, readable, right? Analytic function. How many of you have heard this name or? Anyone has heard this before?
Sounds maybe familiar, but I don't
I
know.
don't think so.
You don't, Jordan, Alia?
Yes, me too.
You have heard it. Yes or no?
Yeah.
Yes. Okay. Jordan, you said you heard it or no? I thought you said
No.
no. Michael?
I don't think so.
Duke?
Yeah, I have.
Yeah. And Moses?
I wouldn't say that I have.
Khalid? Yeah, but Khalid, you have seen it before because Khalid, we don't have your video, but that's okay. I'm not asking you to put on the video, but you just.
Yeah, I heard it, doctor. But I have low connection here. I'm sorry for that.
Yeah, no. So sorry. Okay, so analytic function is pretty much a very simplistically speaking, it is the way of saying the derivative of a complex number. That's how the derivative exists, but it is slightly more than that. Right? The two-dimensional thing, it is not just a derivative, it's a very special type of derivative. We will call it isotropic derivative if you want. So let's see what that is, right? So let's, first let's do the normal derivative, right? One dimension, standard derivative, let's call that. Not having a complex number. Let's do it's trivial for you guys. Standard, yeah, it ends with a D. Standard. So one-dimensional function. So we have f is equal to f of x. And let's define what a derivative is. And so this is kind of cyclic argument, but let's say that we know Taylor expansion, then it's kind of, you can define it in one way, but remember that in the very first days, we didn't have Taylor expansion, so it was defined in terms of limits. But the basic idea is that you make a small change in x, so, and look for the change in f. So this is x plus delta x minus f of x. Right? That's a change in the function f divided by x plus delta x minus x, and then you take the limit delta x tends to 0. right? If you were to see this in a geometric way, f and x, so that's your function. And if you're talking about at this point, so that's your x. You go a little further, this is x plus delta x, and you evaluate the function at this point. So this is your f of x, and that's your f of x plus delta x. And this is your slope that comes about if it is in the limit delta x tends to 0. That's a unique coordinate, very straight forward. How would you, let's do one thing here. The denominator is delta x, so the x cancels out. That's delta x. Now, I'm saying there is a Taylor expansion available. Historically speaking, Taylor expansion came after the derivative was defined. So, in that context, you're going. So there's a slight cyclic argument there. But if we know the Taylor expansion, we know that f of x plus delta x, when delta x is not necessarily small, even when it is large, as far as it is, or for most functions, you can define that with those caveat in there. So this is f of x plus delta x times the derivative comes in. So this is partial, actually there's only one variable, it's a total derivative. Right. And let me go one more step. X squared over 2 factorial, second derivative of f squared. Right. Is that Taylor expansion clear? Right, I'm expanding about x. Right. So that's a Taylor expansion, and it keeps going. And then I have to eventually subtract f of x. That's minus of f of x. Okay. Pretty obvious to you guys. Now notice what happens, and this is always happens for every function, that this f of x cancels out. Crucial. And after it cancels out, this delta x cancels this delta x. That's very important. And after you do that cancellation, what we have is limit delta x tends to 0 of f by dx. Notice this cancellation. And whatever is left out is a function of delta x. And now I take the limit. This turns out to be independent of delta x because that cancelled out. The second one is not. In fact, all higher terms will have a delta x. That goes to 0, exactly goes to 0, important. And this is exactly df by dx. An exact statement, it's not an approximation. And even though it seems like Taylor expansion, we are actually approximating only for small delta x, this works. But in the limit delta x tends to 0, this is an exact statement.
So what happened to your delta x again? Can you explain that to me?
Which term, here or here?
Yeah,
So,
that one. Mm-hmm.
I canceled this delta x.
Oh, okay. I wrote it again. I gotcha.
Yeah. That cancellation is important. It's only the first term that survives. After, or the second term, right? First term gets cancelled. The second term has a delta x that gets cancelled, or sorry, that survives, and rest everything has a delta x which will go away in the limit. So that's crucial. Right? Get that picture clear. And now we are going to extend this on the complex plane. And that will be interesting thing that it will turn out that it is not unique. Then we will make it unique. Okay, is that clear? Any questions, comments? Okay, so let's do exactly the same thing and on a complex plane. Okay. So we want to talk about a complex function f of z. So let me go slow. Yeah, f is f of z, right? That's how it's write it like that. And remember, review a little bit. Z is x plus iy, which is having a diagrammatic representation of x being the real part, y being the imaginary part of the complex number z. And if you have a function f of z, it is always possible to write it. So since this is a function of x and y, and you can always write it as a real function u of x, y plus I times v of x, y. That's because we defined algebra, right? Addition, subtraction, multiplication, division. Always it is possible to get I separated out. Like every complex number can be written as a real part plus an imaginary part times I. Right. So that's our built up. So basically, it is now hard to draw a picture, right? Earlier, x and y, one-dimensional quantity, x was your x-axis, and then on the y-axis you show the function. But now you have a two-dimensional quantity. From this, you're going into another complex plane where this is u and this is v. Right? That's your f of z. So that's the best way to visualize it because you cannot show all of it. And now you want to define a derivative, right? Let's say you have a point here. That's your complex number z. And how will you define a derivative? You make a small change in the domain. So I go from here somewhere else, right? But now this is not unique, right? I can go here, 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 anywhere. It can be anywhere on the plane. And then I find, so this point could be going somewhere here. And this point could be going somewhere there. That's the change in the function due to the small change. Right? And I want to see in the limit when that approaches the original point, what is the derivative? That's the idea I'm going to put in. So that's your function. So we want to define our derivative, right? The f by z. That's my goal. And I'm going to define it the following way. Use the same idea as earlier. I'm going to first define my delta z. So I would say z is x plus iy. So it is x plus delta x plus y plus delta y. And that has been I. So that's my change in my domain and subtract the original. So is that clear? That's my delta z if you want. Delta z. So this has this definition that delta z is equal to delta x plus I times delta y. Make a small change on the domain. So this will be, this is my delta x and that's my delta y. And look for the change on the complex plane. Here, function f is u of xy. So I would say this is u of x plus delta x, y plus delta y, plus I times v of x plus delta x, y plus delta y, and subtract out u of xy plus I times v of xy. And then I have to take the limit. Delta z is this, right? That means there are two quantities. I've said delta x tends to 0 and delta y tends to 0. Or it is equivalent to saying delta z tends to 0. That's going to be my definition of derivative if I go exactly in the same spirit as my earlier one-dimensional analog. Okay, well, that should be straightforward. And let's see what happens, right? Let's bluntly substitute this Taylor expand as we did. This is a two-dimensional Taylor expansion, but that's not very hard, right? Two-dimensional is two separate one-dimensional expansions. So if that is not familiar, just let's review that. So f of x plus delta x, y plus delta y. So this is u and v, but in general there is something like this. Expand one of them, right? So keep the x the same. So this is f of x plus delta x, comma y plus delta y times, this time it's partial derivative of the function with respect to y. And just to clarify that this is at x plus delta x so, and this is at y. Is that clear? So I expanded only in y, and there are higher terms actually. But let's stick to leading order. Then expand in x now. So this is f of x comma y plus delta x of derivative of f with respect to x now of x comma y. But I can expand this also. Plus, go down. Plus, maybe I can fit in there. Plus delta y d by dy of f of xy plus delta x and the original dot also stick. Hopefully that's clear. And this will involve xy plus delta x. This is now f x comma y. The same thing with delta y. And the next term has two deltas, right? Delta x and a delta y. Right. And let's just say by saying that this is order square. Order delta x square, delta x or delta y square. Is that clear? Any questions on that? Because I'm going to use that. So use that in here, limit. Let me write this as delta z tends to 0. That means that delta x and delta y has to independently go to 0. The denominator x and y cancel out, so there's only delta x and delta y. Let me explicitly write that. That's delta x plus I delta y, which is nothing but delta z. And like earlier, I would like that to cancel out, right? The leading derivative will be, which is independent of the delta x and delta y. Okay, so now what is this? Let's expand that out. I have the expression there. So this is u of x comma y plus I, sorry, no I, right? How is this? Delta x, sorry. Delta x times partial derivative of u with respect to x plus delta y partial derivative of u with respect to y, and there are higher orders, right? So which all I'll collect on the on one end, and there is minus of u of x also. So this is minus of u of x, and all these derivatives are taken at x comma y. Plus I times same thing for v plus delta x and minus of v of xy.
What is that in front of the bracket? It looks like a
I.
C.
I.
Okay, okay, okay.
That's I here. And there are higher order terms, right? Let me just write it as order square. Okay. Clearly the u cancels out and the v cancels out. Right? And I can write this as, so that we rewrite this in the following manner. Limit delta z tends to 0, 1 over delta x plus I delta y. I want to write it in a particular form. What is that? So I can write delta x here. So this is delta x. And there are two terms for that. I'll put that as du by dx plus I times dv by dx. And the same thing for dy, but I want to, since I have this I dy there, so I want to add and subtract, or I can actually put this term first, right? That is the best way to put this. So plus I times delta y times, since I've taken out an I, so I have to introduce an I there. That's minus I times, yeah. Should I write it the other way? Maybe write it the other way. So this is dv by dy minus I du by dy. Plus order square, right? The second order quantities. Okay, that should be clear.
So can you just factor out the function then?
Which
Delta x plus I delta y or whatever?
that's a question. That's a question, right? If you would like, yeah, good point. If you want the derivative to exist, right, you would like that cancellation. Agreed? Otherwise, derivative doesn't exist. It's not unique. This cancellation doesn't happen. Delta x doesn't, this doesn't come out, right? Is that clear? I think exactly what you're pointing out, it doesn't come out. So derivative doesn't exist on a complex limit. At least the way we wanted it to, define it. You can say it's a, yeah, if you come in certain form, yeah, I don't know, yeah. That's not okay, correct? But now let's put the condition that I want to cancel. There is a special case under which I can actually take this common, and that is when this is equal to this. That's a possibility, right? But that's not a normal function. That's a very special function with some constraints. In general, it doesn't work out. But there are some functions where this is exactly equal to this. So let's, let du by dx plus I dv by dx be equal to dv by dy minus I du by dy. Right? That's that two quantities in the parentheses. No reason to take that except that we want to define our derivative in such a way that that cancels out. If that is the case, then I can just take this out. That cancellation happens. Second order in the limit goes to 0, and suddenly you have a very unique derivative. It is either this or that, right? Once this comes out, then it is either this or that. So this is either du by dx plus I du by x is also equal to dv by dy minus I du by dy.
What kind of function is that?
That's called an analytic function.
Okay.
That's an analytic function, right? Any function that satisfies this is called an analytic function, and is a very powerful. It's a very constrained function. It's not a normal function, right? You rarely find it, but if it satisfies this, then it has a lot of special properties because it has a derivative. Then, right? In this way, we can define a unique derivative. In fact, notice what this is. this is independent of actually how you approach the point. It's not that you cannot define, you could have always defined the derivative, or maybe you would say in 2 dimensions you do define gradient, right? Like gradient is defined as I d by dx plus I d by dy, right? And that's also in a 2-dimensional plane. You do derive a derivative in those in a 2-dimensional plane. But notice what kind of derivative that is. What you do is, given a delta x, if you say delta x, I'll give you a derivative. If you give me a delta y, I'll give you a derivative. Combination, I'll give you a derivative. But each point has an independent derivative. It's not unique. Here, what we are saying is that always this combination, independent of what it is, it's not that delta x and delta y are separate. It is delta x plus I delta y. It's kind of saying, or the correct way of saying this is that it is independent of the direction in which it approaches. And if you have this complex plane, and this is your point z, where you approach from doesn't matter. And this will be called an isotropic derivative. And let me clarify this a little bit. So first, before I go to all those interpretations, let me.
So for these functions, do the typical rules of derivative apply, or do you always have to take the limit? Like you have to use.
We can. No, it's like the standard 1-dimensional case, right? Derivative is defined using the limit, but then you notice some rules. You actually don't have to take the limit. If you obey those rules, that's good enough. Same thing on the complex plane. Always it is defined using this limit, but you will see that once you get, for example, the standard derivative formulas work on a complex plane. If that's what you, did I answer your question?
Mm-hmm. Yeah.
So, I think I pointed out clearly that this is a specialty in there, and these are called Cauchy-Riemann conditions.
I guess to rephrase my question, it seems like when you take the derivative of something, you're always going to end up with like a delta of that function. So you're going to have like, you know, z squared is going to be like 2z plus delta z. So
Yes.
you're just saying delta z is
Mm-hmm.
it's very small always, that you're always making the smallest change possible. Like, so as delta z approaches 0, it's just equal to 2z. So that's the rule.
Yes. So if you're asking this, d by dz of z raised to n will be n times z raised to n minus 1. Yes.
Okay.
Rules apply. But each of this, now you are verifying principle, right? You should actually check this out. But the idea is that, yeah, if it's an analytic function, it is. So how do we check that something is an analytic function or not, right? So actually the answer to your question is, yeah, so here is the answer, correct answer. Right? Yes, all these rules apply if it is an analytic function. How do you check whether something is an analytic function or not?
Those terms are equal.
Yes, you have to verify the Cauchy-Riemann conditions, correct? So let's see what the Cauchy-Riemann conditions are in more clarity. This is a complex function equal to a complex function, right? So it's real has to be equal, imaginary has to be equal. So Cauchy-Riemann conditions are du by dx is equal to du by dy. So a good way of remembering is that this is du by dy and dv of dx and dv over dy, right? So there are 4 possibilities, right? This is equal, and this has a negative sign in it. So this one, so how do you put a negative sign in So this one has a negative sign, whatever that means. Okay. Is that clear what I meant?
Yes.
Explicitly say that. So du by dx is equal to dv by y, and du by dy is equal to minus dv. So this is a mnemonic to remember those Cauchy-Riemann conditions. Okay. And now, so what is an analytic function? I should be a little more careful. These are not sufficient conditions. These are necessary conditions, but not sufficient. If you satisfy these conditions, then you can be sure that at least, or if it doesn't satisfy the conditions, you're sure that it's not an analytic function. But if it satisfies the condition, then you're not very sure because there are still that could it needs to satisfy the continuity conditions also, or more importantly, the isotropic derivative. And again, in your homework, you will see an example that it is, and we'll do it here also. Some examples of how Cauchy-Riemann conditions do not completely give you. But first, let's do some simple exercises where we see Cauchy-Riemann conditions alone. Right? So maybe I start. Yeah, I still have time. Yeah. So let's do a simple example. Z squared. Right? That was an example that Jordan pointed out. So let's say f of z of f. Let me just write f. I'm not writing f of z with a purpose. I'll come to that in a few minutes. So f is z squared. So write it in terms of u and v. So x plus iy the whole square, right? And this tells me that it is what? So it is x squared minus y squared. And then that is 2 times I times 2x squared. So my u is right here. The u is x squared minus y squared, and v is 2 times x squared. Do the derivative with respect to x. Du by dx is equal to 2x, and du by dy is equal to minus 2y. What about here? dv by dx is equal to 2y, and dv by dy is equal to 2 times x. And clearly, this is the same, and this has a negative sign associated with it. Right? So it satisfies Cauchy-Riemann conditions, and it turns out that this is also analytic everywhere except you can say at infinity. Right? At infinity is infinite. So at infinity there is a challenge, but then at infinity is not part of the complex plane anyway, so we don't worry about it. So it's analytic everywhere. So you usually don't say just an analytic function. You have to say, is it analytic at a certain point? That's what is more important. Okay. So that's okay. So better to come up with an example. It does not satisfy. Any examples that you can think of that does not satisfy that immediately out of your head? Do you guys have any interpretations? Feel for this?
What about like cosine?
Cosine of z?
Yeah.
Yeah, let's try that. So cosine of z, f is cosine of z, right? So that's cosine of x plus iy, right? Break it up because we want to separate I and I separately. So this is cosine of x, cosine of iy, right? Minus of sine of x, sine of iy. Cosine of iy is what?
I times
So cosine of iy is equal to exponential of I times iy. So cosine of theta is e raised to I theta plus e raised to minus I theta over 2. That's I times y plus e raised to minus I times y over 2. So this becomes e raised to minus y, and that's plus e raised to y over 2. But that's nothing but cosine hyperbolic y, correct? That's cosine hyperbolic y. Okay? Like that's a definition of cosine hyperbolic.
mm-hmm.
So that's okay. So now we have cosine of x times cosine hyperbolic of y. And same thing with sine of iy. That comes out with a factor of I actually. So let's see. The exact plus or minus it. So sine of iy is equal to exponential of I times iy minus of exponential of minus iy divided by 2 times I. There's an I there, and there's a negative sign. So this is e raised to minus y minus of e raised to y over 2 times I. There is no I in the definition of sine hyperbolic function, and this comes with an opposite sign. So there is a minus 1 over I of sine hyperbolic of y, which is the same as I times sine hyperbolic. Okay, so that's good. So we got the I then, right? So this is minus I times sine x times sine hyperbolic of y. Okay. So your u is cosine x cosine hyperbolic y, and v is minus sine x sine hyperbolic y. Right. Again, do the same idea. The u by dx is now x is only here, so it's minus sine x cosine hyperbolic y, u by dy. That's derivative of hyperbolic functions have no plus minus issues there. So it is simply cosine of x times sine hyperbolic y. And the v by dx is minus the sine of x sine hyperbolic y, and the v by dy is equal to minus sine x sine hyperbolic y. And if you notice, it satisfies Riemann Cauchy-Riemann conditions. That's actually an analytic function.
But would sine satisfy the same condition since it's not?
Yes, sine of z also satisfies conditions. So apparently f is equal to sine of z. Again, I have not said that it is analytic. To verify the analyticity, you have to actually there is no straightforward condition to do that. But at least it satisfies Riemann Cauchy-Riemann condition, and this is analytic. Just for information, this is analytic. This is also analytic function. So what might not satisfy?
Hmm.
Let's do this example. F is equal.
So could conjugates, because they contain I, would they not satisfy?
Conjugates, yeah, that's a good point. Yeah, conjugates. Yeah, think of it.
Be-
Yeah, good. Uh-huh.
Because they have an I term. So those I terms, whenever you do,
Yeah, you have a good point, a very good point. But it's, yeah, I don't know what you mean by I, but let's see. So the simplest conjugate, since you mentioned conjugate, I was going to do another example. But let's take conjugate, right? So Z star, let's say, right? The simplest function you can think of, what are the simplest functions you can think of, right? On a complex f of Z times is equal to, or first let's say Z, right? Maybe that's what you're trying to think, right? Let's do Z, this is X plus IY, right?
mm-hmm.
So U is equal to X, V is equal to Y. U by dx is equal to 1. U by dy is equal to 0. V by dx is equal to 0. And dv by dy is equal to 1. Right? So maybe you suggest that this may not work if it is Z star. I think that's what you are having in mind.
Yep, exactly.
E is equal to X and V is equal to minus Y, right? And du by dx is equal to 1. This stays the same. This stays the same. But now dv by dy
Negative one.
equals to negative 1. This doesn't work. That doesn't work. So f of z star is not an unknown. This is not an unknown. Remember, if it doesn't satisfy continuum immediately, you say that. And it's everywhere, right? That means not just a special point. Everywhere it doesn't satisfy. In fact, that seems to suggest that, oh, so that's a complex, that's the simplest function you can think of. And now let's do f. Any complex function in general depends on x and y, right? So it's f of z basically, but x and y. So there are two variables which you can think of as z and z star. So either you write it in terms of x and y, or you can write it in terms of z and z star. That's also a valid coordinates if you want, right? And then let's see what it means. So I want to write everything in terms of z and z star. So when I have a function f, this is u of xy plus I times v of xy. So I can write it in terms of z, and so this is u prime of z comma z star, if you want, plus I times v of z comma z star. Always a possibility of You can always do that. But then what about the Cauchy-Riemann condition, right? What does it mean? So let's think of how should I state this? Yeah. So where's this? This. Fine. So let's do the derivative. So remember, f is f of z comma z star. And let's find out what is the f by dz equal to. Df by dz will be equal to, since z and z star have x and y dependence in it, so chain rule, right? So I can take the derivative with respect to x, and then take the derivative with y. The chain rule for partial derivative. That's good enough. F is u plus iv, right? So this is dx by dz times du by dx plus I times dv by dx plus d by dz, and this is du by dy plus I times dv. Basically, what I'm trying to do is trying to get the Cauchy-Riemann conditions in terms of z and z star, simply because the star did not work out, right? Maybe that is a simplicity in seeing the Cauchy-Riemann conditions in that language. Z is equal to x plus iy, and z star is equal to x minus iy. That means to say that x is equal to, if I add this, z plus z star over 2, that's my x, and y is equal to z minus z star over 2 times I. That tells me that dx by dz is 1 by 2. This is 1 by 2 times du by dx plus I times dv by x plus dy by dz is 1 over 2i. Put the real and imaginary terms together. So this is 1 by 2 times du by dx, and here this cancels out, plus dv by dy. And the I term is I of 1 by 2 times dv by dx, and this one I wrote, and this one, right? So this is minus of du by dy. But Cauchy-Riemann condition tells me that these two are the same. So that's nothing but du by dx plus I times dv by dx, because these two terms are exactly the same. So that's my derivative with respect to z. Okay, I don't learn much except that earlier we said this was our derivative, right? So derivative with respect to z apparently gives you the total derivative. But what does that mean? Let me now do what is df by dz star. So this is where I will learn something about the functional dependence on Z star. It seems like this is to get an insight of this, you have to go back and look at the definition of the derivative. Like the last line, we wrote the definition of the derivative right after we defined the isotropic derivative, and that's exactly this. So the derivative of a function is exactly this, but we know that there is another partial derivative, Z star. What happens to that? So again, do the same thing. This is dx by dz star, f by dx, plus dy over dz star of df over dy. Dx over dz star here is 1 by 2. And df by dx is du by dx plus I times dv by dx. That's the same. But now dy by dz star is minus 1 over 2i times du by dy plus I dv by dy. And again, let's put things together. 1 by 2 u by dx, and the I cancels out here, and this is minus dv by dy, and plus I times 1 by 2 dv by dx, and I is, if I take the I upstairs, that's plus du by dy. Now, if I use the Cauchy-Riemann conditions, you see that earlier they added up. Right? These two terms come exactly with the opposite sign. This is 0. And this is also 0. Means that this is 0. So, how do you see Cauchy-Riemann conditions in a function? It should not have a Z star at all. So the Cauchy-Riemann conditions, which was slightly not very intuitive earlier, has a slightly better form here. And it says that the partial derivative with Z star should be equal to 0. That means to say that it should not have Z star at all. So it should not have Z star, so it's only Z. So that's why you'll always see a complex function, you always write just Z, right? You should have asked earlier, oh, why not Z star? But because whenever you put a Z star, it's not a good function. It's not a useful function, put it like that. Okay. So very straightforward. We are looking at a function, deciding whether it has a chance of having it analytic or not. If there's a Z star, right away, off the bat, you say that, oh, that's not analytic. But if it is a function of Z, then you have to be careful. Then you have to analyze. First of all, Cauchy-Riemann conditions are satisfied, but then you have to satisfy, or I don't know, conditions after that. You just have to make sure that the continuity conditions work, and we'll come to that later. So, what is an analytic function? An analytic function has to satisfy Cauchy-Riemann conditions, and more beautifully, it has a lot of good properties that we will see, pretty much like electrodynamics, electric field and electric potential, curl-free quantities. So this will be having a physical interpretation of that kind, and we will see. For now, we'll stop. These quantities are pretty much there in any complex analysis book, but Morse and Fishback does a good job of it. And pretty much all the notations are, I think, still valid. That's one small recommendation. Yeah. Erskine also does a good job. Thank you.
Thank you.
Thanks.
Thank you.
Bye.
Bye.
So real quick, when you
Yes.
take the derivative of a real function, you get like local characteristics about it, right? Like
Mhm. Yeah.
so like when you Taylor expand, it gives you about that at a
Mhm.
local sense.
Yeah.
What happens for a complex function where
It's the same thing. Okay, so the way to look at it is that if you know the, like, how do we think of a function in terms of its derivative? If I know the function and all its derivative, I pretty much know the function completely. Is that clear what I mean?
yeah,
Like, you don't have a choice. Once I tell that the first derivative is this, second derivative is this, third derivative is this, it pretty much decides the value of the function all the way till infinite. Right?
yeah,
Now think of a complex plane and imagine a surface on it, which it's not a surface, it's a four-dimensional quantity, right? Think of a complex function and now decide that, okay, if it's an analytic function, if I know all its derivative at one point, that complex function is completely decided. That's not the case if it's non-analytic. Then there is a lot of independence. So it's a constrained function in ways, in that sense.
okay.
In fact, what we will show is that u and v, that f function is u and v, right? If I specify my u, v also gets specified. V is not independent of u.
So are U and V just harmonics of some sort, like
What do you mean by harmonic? Yeah, that's correct. That's a
just like an oscillating functions?
uh, okay. By harmonics, usually the language here is that it satisfies the Laplacian.
Satisfies the Laplace. So it's not like spherical harmonics. It's like
Yes, exactly.
okay.
So, I mean, actually, why is spherical harmonics called spherical harmonics? Because they satisfy the Laplacian. Okay, so yeah, they are oscillatory. They turn out to be oscillatory, but that's not the requirement. It should satisfy the Laplacian. That's the main thing.
Okay.
And that gives the connection with the electrodynamics. Electrodynamics has Laplacian as electrostatics, right? So any electrostatics problem in 2-dimension can be represented using a analytic function. We will see that. It's kind of a beautiful thing. Like in electrostatics also, there's a lot of constraint in the sense that electric field has to satisfy the divergence and the curl has to be 0. Right? So those are the conditions, but we are going to bring it down to 2 dimensions and then think of it in that spirit. But that's going farther than what we are at. Like we'll come to that next
So
week.
and then my next question is like, so locality of say the not the cross product, but the curl of a vector field. Like when you go to 0, your vector becomes infinite, right?
Not necessarily, only for point charges, right? Not the curl. Curl actually doesn't go to 0.
Not the curl, the divergence. Sorry.
Divergence for a point charge goes to 0. And that will, so what we will say is that in that context, what we will say is that at that point, it is non-analytic. Only at that point.
But how do you find that from this definition?
So this definition will not give you, because this only tells you this is a necessary condition. It's not a sufficient condition, right? Sufficient condition is coming from experience. There is no standard one, there's no prescription, if you want to say. There is no simple way of looking at it. But mostly what will happen is that if it is infinity at some point, that's the way to look at it. And even if it is infinity, one has to look at it as, or think of it like this, derivative from all directions should be the same. That's our condition. Does that help?
Mm-hmm. I'm just thinking like if you do the limit of some function, you end up with infinity over infinity. And then
Yeah.
you do like the L'Hopital's or whatever, L'Hopital or rule.
If you get the same infinity, you're good, right? But it will turn out that it's not. Like that's so the key feature of analytic function is that its derivative should be independent of the path from where you're coming from. That's what we call it isotropic derivative, right? So first you check that, okay, Cauchy-Riemann conditions are satisfied. That's surely one, it takes away most of the functions are removed out of that. Once that satisfies, you have to still check, oh, is it still isotropic? And you will see that even functions that satisfy Cauchy-Riemann conditions, they need not be having isotropic derivative. So that's the caveat in that. So it's that's what brings in that, what is it? The moment it's not algebraic, then it takes away a little bit of simplicity in there. You have to have a lot of experience to see this. So that's the challenge. But we will notice that at least the simple non-analyticity can be captured just by looking at whether it is going to infinity. Okay, we'll see that.
Okay.
Good points. Yeah.
Thank you.
Okay.
Welcome back.
Bye-bye.
Take care.
Bye.
Guys. Yeah. Bye, Michael. Bye, Moses.
You.
See ya.
Bye, Talia.
Bye.